Welcome back. Let's continue on chapter 6. Today we're going to focus on section 6, inverse trigonometric functions. Let's start with a short review of some of these trigonometric functions. For example, the sine function. If you remember, sine x would look like a periodic function, and it will look like something like this. Continuing over a period of 2 pi, it will repeat itself. So you will get the same graph over and over on both sides. This would be here pi, there is 2 pi, and so on. Maybe I should have, let me redraw this just for a certain reason. Okay. It would be a bit easier to graph. Okay, so here, let's assume this is a period of 2 pi, and similarly you would expect the same thing over on the left side and continuously. The heights are supposed to be equal, 1. Height supposed to be the same as that, 1, and here this y value is -1. Okay. Why do we care about the trigonometric function is that the inverse trigonometric function is that they're useful tools to calculate certain integrals. Some integral turns out to be exactly the inverse of a trigonometric function. So we need to learn these as we go on as well. So here, let's focus on the fact that if you want to talk about the inverse function, you expect to have a one-to-one function. But if you look at the sine, it's not a one-to-one function, because if you draw a horizontal line, it crosses multiple times. It's supposed to cross once. So to have a one-to-one function, normally we cut off the parts of the graph that creates multiple y values. So in this case, if I only focus on this part of the curve, if I only focus on this section and stop at these points, and do not continue, then the graph, this red graph, is a one-to-one graph. If you ignore the blue curves, now what do you have is a one-to-one graph. It's not the sine function all over the domain that is supposed to have from -infinity to infinity. It's over a restricted domain. So what I can do is I can graph this better over the restricted domain. And what is that restricted domain? That restricted domain is just to make sure the function is one-to-one. That means every x value has a specific 1 y value. So the sine over that restricted domain is here up to pi over 2, and on the other side to -pi over 2. If you only focus on this part of the sine function, what we notice is that this is a one-to-one function. So therefore, it is possible to talk about the inverse. And if I ask you to graph the inverse, you don't need to know the function. You should be able to simply graph the inverse by reflecting it. And reflecting it about the line y equal to x, about this red dotted line. You can graph the inverse. You can graph the inverse function. And what would be the inverse function? If you reflect it, we'll get something maybe like here. I'm not as accurate as I hope to be, but just if you drew the reflection, this is what you would get. And these points will change each other. So this would be from -pi½ go up to pi½ and on the other side you would have 1 and -1. X and y values will change. And what do we call that inverse function? This green function is what we called sine inverse. Is an inverse function. Another notation for it is arc sine. Arc is just a representation of the inverse. This -1 doesn't mean to the power -1 again. It's an inverse notation. And so what does it do? The inverse function takes an input. What is that input? It's the corresponding y value of what do you have for sine. So for example, if I know sine of pi over 4 is √2/2, then what does sine inverse do? Sine inverse takes in this as an input. It takes the root 2 over 2 as an input. And what does it give me? It gives me pi over 4. The only thing is, you should notice that if, for example, we know sine 5 pi over 4 is root 2 over 2, in this case, change this to sine 9 pi over 4 is root 2 over 2, then the inverse will give you pi over 4. It should give you a value between pi half and negative pi half. It will give you a value in this, or correspond to its range from negative pi half to pi half. It should never, this value out here, it should never be above pi half or below negative pi half. In the same way, the input to the sine inverse, corresponding y value for the sine function. What was the range of the sine function? The range of the sine function was 1 to negative 1. That means the domain of the sine inverse is 1 to negative 1. Negative 1 to 1. It means if I'm talking about the sine inverse, so these are the restrictions. I'm talking about the sine inverse as a function. X value, the input, must be between negative and 1 to 1. And the outcome is in the restricted domain, is negative pi half to pi. Okay, it's important to follow these. So here, for example, sine inverse of 1/2. So you ask yourself, okay, what does sine inverse of 1/2 mean? This means, what is that angle? Theta is an angle. That is, what is that angle that sine theta equals to 1/2? This is the same question. And if you ask yourself this, you should look for the angle in this range, between negative pi half to pi half. This is the range that you should focus on. Nothing else. Outside that, it's not possible, because it would not be a one-to-one function. We specifically picked the domain to be this. So where do we get sine to be pi over 2? 1/2, sorry. You can, if you forget it, you can always go back to unit circle. And the restricted domain tells you you're allowed from negative pi half to positive pi half in this section. What does sine represent? Sine represents the corresponding y value. Where do you get the y value to be 1/2? At a certain angle, that angle turns out to be pi over 6. So theta turns out to be pi over 6. So I can say this is pi over 6. Okay. It's important that you understand the concept of inverse. This is something that you should be familiar with from earlier classes, but reminding you of this inverse function is important. Okay. How about if it's combined with other functions? How about tangent of sine inverse of square root of 2 over 2? It doesn't really matter. You can simplify sometimes the inside and answer the question then later. What is tangent of? What is sine inverse of root 2 over 2? For what angle sine will give you root 2 over 2? That angle turns out to be pi over 4. At 45 degrees, here we already answered this. At 45 degrees, or pi over 4, the sine inverse of root 2 over 2 is pi over 4. And answer this question, what is tangent at pi over 4? Simply 1. Okay? This technique, in this case, works, but not always. Sometimes it is not possible to find the inverse properly. So in this case, if I ask you what is the tangent of arc sine of 1/3, you don't know what is this angle. Exact value you don't know. You can use a calculator to find it, but it's going to give you a decimal value. That's not a proper way to find it. So there's a trick to calculate these type of compositions. So let's call this arc sine 1/3 as theta. We will use this idea in next chapter when we're going to talk about the integral of using the inverse trigonometric functions to calculate the specific types of integrals. I'm just going to introduce this idea now. So let's say we want to find out tangent arc sine of 1/3. And we don't know arc sine of 1/3 precisely, like sine inverse of root 2 over 2. We knew that one is pi over 4. That's why we could easily calculate it. In this case, let's say we don't know arc sine of 1/3. And we call that result, whatever arc sine of 1/3 is, we call that to be some angle, theta. This is the technique. Okay, so what is the property of theta? If arc sine of 1/3 equals theta, then what is sine theta? Sine theta must be 1/3. This is what we know. The inverse at 1/3 is theta, so therefore sine of theta must be 1/3. Or if you don't, there is a step in between that if you don't recognize, is if you take a sine from both sides of the equality, what you get is a composition. Sine with its inverse. It's the same as saying square root with x squared. What you get at the end is these two will cancel out, and what you get is exactly just simply x. So here, these two are inverses of each other. So they will cancel out each other and you will get only 1/3 left. On the other side, you have sine theta. So sine theta must be equal to 1/3. This is what we learn. And what does that mean? Sine theta equals to 1/3. That means if you have a triangle in triangle form, the right triangle, if I call this theta, what do I know is sine theta, which is supposed to be, by definition, opposite divided by hypotenuse. So it would be 1 divided by 3. This is supposed to be the opposite length. That is supposed to be the hypotenuse. So I can find out then what is the other side of this right triangle by Pythagorean identity. It would be 3 squared minus 1 squared, which would be square root of 8. This is by Pythagorean identity. You can figure out this length. You should say 1 squared plus something squared, you can call it x, equals 3 squared. So therefore x would be simply square root of 8. That's how I found the square root of 8. And what do we know? We know that this triangle, so therefore we have some information. What is the question asking? It's asking to find out what is tangent of theta, because we call this thing theta. If you have this triangle, you can answer that. What is tangent theta? By definition, tangent is supposed to be opposite divided by adjacent. So therefore, tangent must be 1 divided by square root of 8. So this technique gave us the answer. You could have used it for the square root of 2 over 2 as well. In that case, what you get is a triangle, or this length is root 2, this length is root 2, this is 2. So therefore, tangent would be root 2 divided by root 2, which is simply 1. But it wasn't necessary in that case, because we knew what was the sine inverse at root 2 over 2 simply. Okay? This is a kind of a technique that we will use often. Okay. Now that we know a bit about the inverse, let's talk about the derivative of it. I'm gonna kind of prove the derivative for sine inverse, then we built on that for cosine inverse, tangent inverse, and so on. It would be the same technique again. Okay, so let's focus on how to find the derivative of sine inverse. I've already written the derivative, but let's say we don't know this. And they ask you find out what is the derivative of sine inverse of x. So let's assume we know y equals sine inverse of x. And they ask you find out dy over dx. What do we do in this case? If you remember, for the general exponential, we applied an ln trick. Here, the trick would be to get rid of that sine inverse, because we don't know the derivative. So how do you get rid of the sine inverse? Is you apply the sine to both sides. So you say sine of y equals sine of sine inverse of x. If I do that, what do I get? Left side, still sine y. What do I have on the right side is the composition of sine with its inverse. So therefore, these two will cancel out and I will get simply x. So I have this equation sine y equal to x. Can I take the derivative here? Yes, because I know the derivative of each term. Derivative of, so therefore d over dx would be give me sine, let me write this as the derivative of sine y would be cosine y multiplied by dy over dx. And on the other side, derivative of x would be simply 1. So therefore, I can find out what is dy over dx. Is 1 divided by cosine y. This is the derivative. You may ask what? This is not the same as that, and you're correct. Because now the derivative is a function of y, not the function of x. So somehow we should get rid of this y in here. The cosine is okay as long as it doesn't involve y. So how do we get rid of that y? Let's do that. We'll go back to what we knew. We know this is the same as 1 divided by cosine. Instead of y, we can replace y with sine inverse of x. Sine inverse of x. And now, this is the derivative. So 1 divided by cosine sine inverse of x. And it's a function of x. And you may ask again, why are these two not the same? The reason is we can simplify this by the same technique that we talked about last time. So let's draw a triangle. What do we know about sine inverse of x? We call it y. So we assume this angle is y. So sine inverse of x is, sine of y is x. So if this is the angle y, it's supposed to be x divided by 1, opposite divided by hypotenuse. This must be x, that must be hypotenuse, must be 1. Sine of y must be x divided by 1, which is x. So therefore you can find this length. This length is simply 1 minus x squared if you apply Pythagorean rule. So here, dy over dx equals 1 divided by, what is cosine of sine inverse of x? It is the same as saying 1 over cosine of y again. What in this case, we can answer what is cosine of y. Cosine of y would be, using the triangle, it would be 1 divided by adjacent. So 1 divided by, the adjacent divided by hypotenuse. It will be square root of 1 minus x squared divided by 1. Divided by hypotenuse, which is 1. In this case, the 1 doesn't really affect anything. And now you see that these two are the same thing. So we can say, okay, if you want to take a derivative of sine inverse of x, you don't need to go through these over and over. What you can say is simply it would be 1 divided by square root of 1 minus x squared. Okay, so this was a kind of a proof of the derivative for sine inverse. So let's apply that to some examples. What would be the derivative of sine inverse of x squared? If instead of x, what if it was x squared? Again, this would be a chain rule. You assume that this is a u and apply the derivative to sine inverse of u. What would be the derivative? It would be 1 divided by square root of 1 minus u squared. In this case, u is x. So x squared squared, because this is supposed to be u. The d over d of sine inverse of u over dx would be 1 divided by square root of 1 minus u squared multiplied by du over dx. This is the chain rule. So multiply by derivative of x squared with respect to x is simply 2x. That's the derivative. You can turn this into x to the power 4 if you want and put the 2x in the new. How about the next one? What is the derivative of sine inverse of ln x? Again, you can apply the chain rule. This is the input function, u. So what we get is 1 divided by square root of 1 minus ln x squared multiply derivative of ln x derivative, which would be 1 divided by square root of 1 minus ln x squared multiplied by derivative of ln x 1 over x. Change this to. Okay, and what is happening? ln x. Sorry about this. Okay, ln x squared. Nothing complicated as long as you apply the derivative properly. Okay, how about the integration? The integration is kind of tricky, not always trivial, but in trivial cases, if you're given 1 divided by square root of 1 minus x squared, we kind of know that the integral of this is supposed to be the sine inverse function. So sometimes you may see similarities. You may notice the next example kind of doesn't look exactly the same as that, but you notice that square root of 1 minus x to the power 4. If it was x squared, we could have said, okay, this is similar to that sine inverse. In this case, it's not exactly the same, but instead of x to the power 4, if you look at it as, so let me rewrite it this way. If you look at it as square root of 1 minus x squared squared, then what you notice is if I call this a new variable, I have 1 minus, let's say, u squared, and it kind of resembles the sine inverse of u. So what we do is we implement a substitution. Say u equals x squared in this case. So du over dx would be 2x. Therefore, du divided by 2x be dx. And I can rewrite this integral. Go back to color it. Integral would be x divided by square root of 1 minus, instead of x squared we have u, but there is a square still, u squared, multiply by, instead of dx we have du divided by 2x. These x's will cancel out. So what we have is the integral, actually I'm going to put this 1/2 outside, the integral 1 divided by square root of 1 minus u squared d. And that is now 1/2 sine inverse of u plus some constants. Which is the same as 1/2 sine inverse of x squared plus c. That's it. That's the integral. It's not that easy to see what is the substitution. So later on, I will give you an idea how to choose the substitution, the trigonometric substitution, and you don't need to memorize which one is for what. Okay, so at the moment, let's assume we know these integrations kind of have the shape of sine inverse. Okay, that's about it for sine inverse. Similarly, we can discuss the cosine inverse. Cosine inverse requires the domain to be restricted to 0 to pi. That means the corresponding range would be 0 to pi. You have a 1-to-1 function. And again, the inputs are always between -1 and 1 for sine and cosine inverse. You cannot have any number above 1 because sine and cosines are ranged between 1 and -1. And the composition of this cosine with inverse, this is something that I mentioned for the sine, but I didn't wrote it. Sine composed with sine inverse or cosine composed with an inverse, same, it will simplify to x. And the same cosine inverse composed with cosine would be x. The only thing that you should notice is that the domains need to be satisfied. So in this case, the domain of cosine inverse of x, the inputs must be between -1 and 1. Otherwise, the cosine inverse doesn't have any value. Here, domain of cosine x is bounded, restricted to 0 to pi. So you should pick the values from that domain to have exactly x. Okay, so these restriction is kind of required to have these properties. And the derivative, it turns out the derivative is exactly the same as the derivative of sine inverse. The only difference is this negative sign will show up. So that would be the good thing. You don't need to memorize too many stuff. And since this is an online class, there's no memorization required, but it's good to know similarities when there are. Okay, let me mention the tangent inverse as well. Tangent inverse of x equals to y is the same as saying tangent of y equals to x. These are the relation between if f of x equals to y, then f inverse of y equals to x, back and forth. The only good news is that tangent inverse doesn't require the domain to be restricted. So I can put any number that I want inside the tan inverse. I will get a corresponding angle out of it. And the reason for that is, if you look at the graph of tan inverse, so let me draw the graph of tangent maybe first. If you remember the graph of tangent, kind of looks like this. It has a vertical asymptote at negative pi half and pi half. And you will get the same graph over and over. This is for tangent. So what is the inverse gonna look like? So if this is the tangent, if you reflect it, what you would get is kind of this graph. You'll get this as a tangent inverse of x. This is a reflection about the line y equal to x. So what do we know is that there would be horizontal asymptote at pi over 2 and negative pi over 2. And what is the domain? Now I can pick whatever I want because I can pick any x value. There is a y value corresponding to that. Those y values are restricted between negative pi half and pi half. The y values are restricted between negative pi half and pi half. But the x values we pick from whatever we want. And since we already have the graph of tan inverse, maybe I should mention the limits. So here, the limit as x approaches to infinity, positive infinity, what do you get is this corresponding y value of pi half. And if x approaches to negative infinity, this is for tan inverse function. The sine and cosine, there's no infinity limit because the domains are restricted. But for tan inverse, we have these two cases. If x approaches to infinity, if you go in this direction, the y values are approaching pi half. If you're going the other way, the y values are approaching negative pi half. And as for the derivative of tan inverse is 1 divided by square root of 1 plus x squared. The only difference is instead of minus, it turned out to be plus 1 plus x squared. Okay, now that we know these, let me go through a couple of examples just to make sure that we get the idea. So what is tan inverse of negative root 3? If you think about it, tan inverse of root 3 means what is that angle, the tangent at that angle equals to root 3. These two are equivalent to each other. Remember, we turn exponential to log and log to exponential. This is the same relation. So where do we get tangent to be root 3? Tangent is, if you forget, tangent is, you write this, tangent is opposite divided by adjacent, or correspond to x and y. This would be on the unit circle. It would be correspond to y value divided by the x value. The y divided by x ratio must be square root of 3. So somewhere here. That would be the angle. That's what we're looking for. And it turns out that that angle is simply pi over 3. You should double check this through your... oh, this is negative. Sorry, I forgot the negative sign here. Negative root 3, negative root 3. The angle would be on the other side. Sorry. Here we go. Remember the domain. The range is restricted from negative pi half to pi half. So everything should be on the right half of the unit circle. So the angle must be negative pi half. This theta must be in the negative section. So the angle must be negative pi over 3. That's what's important. You should notice that you shouldn't represent the angle in any other way. It should be between negative pi half and pi half. How about the next one? What is tangent of arctangent of 11? Remember, the composition of two functions turns out the inverses of each other, turns out to be the same input as 11. The only thing is that you should make sure that 11 is in the domain of arctangent, and arctangent has domain to be all real numbers. So in this case, this result is simply 11. How about cosine of 2 cosine inverse of 2/3? This doesn't look that easy anymore. We cannot calculate cosine inverse of 2/3 simply. So what we can do is use the same trick that we learned. Cosine of 2, the 2 is still there. I'm gonna call this theta. Theta. So what did we call theta? We called cosine inverse of 2/3. We called it to be theta, which means cosine of theta must be 2/3. So if I draw a right triangle, cosine, which represents the adjacent divided by hypotenuse, that means I have 2 here, this is 3. This is the angle theta. Cosine of theta is defined to be 2 divided by 3, which is adjacent divided by the hypotenuse. So I can figure out what is the other side. I can figure out this length. This length is simply square root of 3 squared minus 2 squared, which is square root of 5. Use Pythagorean identity. Okay, we found out what is the other angle. So what is cosine 2 theta? There is one thing that you should know either from trigonometry, that cosine 2 theta could be written as cosine square theta minus sine square theta. This is one of the identities for cosine 2 theta. If you don't know it, that's okay. You can always look it up. You don't need to memorize these stuff. Cosine 2 theta, this is called the double angle. This is called the double angle identity. Double angle, because it's 2 times whatever the angle was. And now I can say, okay, what is cosine squared? Cosine squared theta is, we have the triangle, use the triangle. It would be 2 divided by 3 squared minus sine is square root of 5 divided by 3 squared. So we found cosine and sine, square them, subtract from each other. Simply you will get -1 divided by 9. Even though it wasn't possible to calculate this in each section separately, you can calculate the combination by going through this triangle. You can double check your work if you have a calculator to see if it's accurate, but some calculator will have round off error, so they will not give you -1/9. On the exams, it is required to show these steps. You cannot just write in the number, because the calculator will calculate that. So it's required to show these steps. Okay, before we go on a bit further, I noticed a mistake, so let me fix that. Here is the mistake. I mentioned that the derivative of tangent inverse is 1 divided by square root of 1 plus x squared. This is 1 divided by 1 plus x squared. There was no square root, sorry. I've written square root so many times that I kind of messed this one up. Okay, so this is the derivative of tan inverse of x. Okay, so we can generalize and say, okay, the derivative of tan inverse of u would be 1 over 1 plus u squared. By chain rule, you should multiply u prime. And here's an example of it. We get the derivative of tan inverse of 2x plus 1 would be 1 divided by 1 plus 2x plus 1 squared multiplied by 2x plus 1 derivative is simply 2. So this is simply 2. So you can write that 2 times this, or you can move it to numerator and say 2 times that. I recommend do it step by step just to avoid making mistakes. And here another one, derivative of cosine inverse, the derivative of sine inverse. Let me shift this up a bit. There we go. What is the derivative of cosine inverse of 1 over x? It would be 1 divided by square root of 1 minus u squared. Actually, for cosine, the derivative was -1 divided by that. So -1 divided by 1 minus u squared, in this case 1 over x squared. Multiply by 1 over x derivative. It's just derivative of 1 over x. You can use quotient rule. You can write it as x to the power -1 on x derivative. Either way, totally fine. You can do this 1 minus 1 over x squared. Multiply by By the way, 1 minus 1 over x squared is going to be written as 1 over 1 minus x squared this way as well. Times the derivative of 1 over x, if you apply quotient rule, you will get negative 1 over x squared. Let's skip that because that's nothing new. And instead of x squared, you can write square root of x to the 4. You may ask, why do you do that? Is because I can now multiply. You have square root times square root, you can multiply the inside. These two are equal to each other. So I can write this as negative 1, will give me positive 1. Square root of x to the 4th times 1 would be x to the 4th. X to the 4th times negative 1 over x squared would be just x squared. And this is it. You can take a factor out an x squared and take an x squared out, but that's good enough here. How about integration? How about we calculate this integral? So what would be this integral? It kind of looks like tangent inverse if we didn't have the 8, if it was 1. But that's not an issue because the 8 is multiplied by. So I can write this 8 times 1 over square root of 3, square root of 3 of 1 over 1 plus x squared. If it's this easy, then you can simply say, okay, this is 8 times tan inverse, the antiderivative, evaluated from 1 over root 3 to root 3. And if you calculate that, 8 tan inverse of root 3 minus 8 tan inverse of 1 over root 3. And then you should figure out what is tan inverse of root 3. For what angle tangent of theta equals root 3? That's what you're looking for. And then for what angle tangent of theta equals positive 1 over root 3? The answer to this one is theta must equal opposite, so this would be pi over 3. And tangent theta equals 1 over root 3 in case theta equals pi over 6. So the inverse of tan inverse of root 3 would be pi over 3. And inverse of 1 over tan inverse of 6 would be pi over 6. 1 over root 3 would be pi over 6. And you can multiply the 8, subtract those, you'll get 8 pi over 6. 4 pi third. Hopefully I didn't make any mistake. But if you found any mistakes, just fix it and write it in the comments. Okay, one more integral. Let me shift this up. This is the type of integral that you should be careful when you're calculating these integrals. You may notice 1 plus x squared in the denominator, but the numerator doesn't simply have 1. It is 1 plus x. So you cannot say this is inverse, tan inverse simply. So what I can do is I can write this as this. There is a common trick. 1 plus x squared could be written as 1 over 1 plus x squared plus x over 1 plus x squared. This is just two different terms, sum of two terms. Now I can answer the antiderivative of this one. Simply it would be tan inverse. The question would be, how do I calculate this antiderivative? So let me write that in two separate integrals. You say write integral 1 over 1 plus x squared dx plus integral x over 1 plus x. Okay, I'm going to calculate each one separately. Integral 1 over 1 plus x squared dx, this is what we learned today, is tan inverse of x plus some constancy. How about the integral of x over 1 plus x squared dx? Well, this one, it's not x times tan inverse. Don't make that mistake. This time, you need to use substitution. What is the substitution? I'll pick the denominator, 1 plus x squared. What do we get is du over dx be 2x. So du divided by 2x equals dx. So I can rewrite this integral as integral x divided by u multiplied by dx is du divided by 2x. And the x's will cancel out. That means that was a proper substitution that we picked. So what we have is 1 over u multiply by du over 2. And you should ask yourself, can I calculate this integral? The answer should be yes. You can take the 1/2 out, and what you have is 1 over u du. And that is simply 1/2 the integral of 1 over u. We learned this last time in 2 sections ago. ln absolute value of u plus some constants. And what is u? U was simply 1 plus x squared. And it didn't need absolute value since 1 plus x squared is always positive. So now what is the answer to this question? It should be tan inverse x plus ln 1 plus x squared plus some constant. So sometimes it is tricky that you need to break up the integral into multiple parts, and some parts may require substitution, some may not. This was an example of those. Okay, I think this is good enough for these 3 types of functions: the sine inverse, cosine inverse, and tan inverse. Similarly, you can define the derivative of secant, cosecant, and cotangent inverse and calculate them. So here is what I mentioned: the inverses, cosecant inverse. The restriction on the input is that the input must be greater than 1. The range of cosecant is always numbers greater than or equal to 1, so the restriction on the domain of cosecant inverse as well as secant inverse, they both have the same restriction. And we've chosen the corresponding range y value. It's chosen to satisfy, to be restricted in the interval of 0 to pi half and pi to 3 pi half. You might ask why they chose this. There's no specific reason. It's just has a nicer form to it, as well as why we originally picked negative pi half to pi half. It was kind of the section that had the 1-to-1 property, and it's a kind of nicest section. It's in the positive part between 0 to 2 pi. How about the cotangent inverse? Cotangent inverse is very similar to tan inverse. Cotangent inverse, there is no restriction on the input. There's no restriction on the x value. X value could be chosen whatever. This could be whatever we want. And the only difference is the y ranges from 0 to pi. For tangent, it was from negative pi half to pi. So for cotangent, it would be from 0 to pi. And the limits, there would be limits. Limit of cotangent inverse as x approaches to infinity. Let me give you a kind of a sketch of the graph. Cotangent kind of looks like this. From 0 to pi. This is pi half in the middle. This is pi, this is 0. So if you reflect it, if you reflect about this line, or the 45-degree line, what do you get is something like that. So as x approaches to infinity, y value is approaching pi. As x approaches to negative infinity, cotangent inverse of x. As x approaches negative infinity, y value will approach 0. It is very similar to tangent. The only difference is the limits are instead of pi half and negative pi half, it's now pi and 0. Try to remember the graphs, they help often. And the derivatives. The derivatives are kind of important too. Derivative of cosecant inverse. Again, you can combine this with cosecant and calculate those through what we learned, implicit differentiation. The derivative of cosecant inverse turns out to be negative 1 divided by x squared minus 1, and there's an x up front. Since the range is all the x is greater than or equal to 1, in this case, x is not allowed to be 1 either because it makes the denominator 0. So all the x's must be greater than 1. Secant inverse, the derivative is very similar to cosecant inverse. These two are very similar. The only difference is again that negative sign. And cotangent inverse, it is -1 divided by x squared, similar to relation between sine inverse and cosine inverse. This is very similar to tangent inverse. It's just a negative. Okay, so let me show you maybe a couple of derivatives and integral for these as well. So here I wrote two examples. The derivative of 1 over secant to -1 of x. The secant inverse, sorry. Sometimes it's better to write arc secant instead of secant inverse just to avoid this -1. Okay, so 1 over secant inverse of square root of x. Think about this derivative. You can write it as, let me write it this way so make sure you understand the question. We're looking for the derivative of 1 divided by arc secant of square root of x. Okay. Just want to differentiate between having a -1 or as an exponent or having an inverse. This -1 here is an inverse, but the 1 divided by arc secant could be written as arc secant square root of x, the whole thing to the power -1. 1 divided by that, you can move it to the numerator with negative exponent. Then take the derivative. What would be the derivative? The derivative would be drag down the exponent, subtract 1 from the exponent. That's applying the power rule. It would be -1 arc secant square root of x to the power -2. Multiply by chain rule, it says multiply by the derivative of inside. So d over dx of arc secant square root of x. Okay, I'm not going to rewrite these, so I'm going to call this. Actually, let me write it one more time, just to make sure. This term, this highlighted section could be written as -1 divided by arc secant of square root of x squared, if we rearrange it. Multiply by, now the derivative of arc secant of square root of x. What is the derivative of arc secant? We learned that the derivative of arc secant, or secant inverse, is 1 divided by. If you see square root of x, square root of x is gonna work as x, but you just assume it's a u. So it would be 1 divided by square root of x, multiply by, I'm implementing it here. Instead of x and x squared, I'm gonna pick, replace it with square root of x. It would be 1 divided by square root of x times square root of x squared minus 1. Multiply by, the chain rule says multiply by the derivative of the inside. The inside in this case is square root of x. So d over dx of square root of x. Okay, these two terms have no derivative anymore. This one has no derivative. We've already taken care of that. This one has no derivative. So you can just assume that you can rewrite those. I'm going to write them as one fraction as well. -1 divided by arc secant square root of x to the power 2. Multiply by square root of x. Multiply by square root of x squared is simply x. So square root of x minus 1. Then times derivative of x, square root of x is square root of x is x to the power 1/2. So the derivative of that would be 1/2 x to the power -1/2, which could be written as 1/2 square root of x. And you can multiply these two and write an x. Okay, this is the derivative. Simplification is not that important at the moment, but you should always try to multiply the terms that you can possibly do. In this case, square root of x and square root of x are just simply x. You multiply them. Okay, how about the next one? What is the integral of 1 over x plus a squared? This kind of reminds me of tangent, if a squared was 1, this would have been tan inverse. But if it's a squared, then it's not that easy to see how do you relate this to tangent. There is a simple trick that we will learn later how to pick proper substitution. But at the moment, I'm going to show you the idea. The idea is, what if I divide everything by a squared everywhere? What do we get? You'll get here 1 over a squared, x squared over a squared, plus a squared over a squared. We haven't changed anything since we divide both numerator and denominator by a squared. So this is still the same equation. The only good part about this is I have 1 over a squared in the numerator. Denominator is x squared over a squared. I can write it as x divided by a squared. This is the same as x squared over squared. And this would be simply 1. By doing that, I just turn this a squared into 1, something plus 1. And the numerator is not that complicated to deal with. This is just a constant. You can write it outside. So I can write this as 1 over a squared integral 1 divided by x over a squared plus 1 dx. Now, you notice there is more similarities in this than from the original function to this tan inverse. So I can say, okay, let's pick a substitution. Let x over a be equal to u. Then what is du over dx? So simply x over a derivative would be 1 over a. So therefore, a du, which equals dx. So the integral, this integral will be 1 over a squared outside, multiply by the integral of 1 divided by u squared plus 1. Now it's similar to the tan inverse, times, instead of dx, you'll have a du. And what is that a du? The a could be moved out again. This is a constant multiply. So a times 1 over a squared would be simply 1 over a. Integral 1 over u squared plus 1 d. And that is now easy to see that it is, the integral is tan inverse of u plus some constants, which means this integral is 1 over a tan inverse of, what was our substitution? X over a plus. So the integral of 1 over x squared plus a squared dx is 1 over a tan inverse of x over a plus c. This sometimes is called the formula that we know as the integral of 1 over x squared plus 1 is tan inverse. They say the integral of 1 over x squared plus a squared is always following this formula. So you don't need to go through these steps over and over. But it's better to know what are the steps. So if you don't always see the pattern, you should go through this process. Make sure that you have some form of the tan inverse derivative. Then use substitution to simplify it as much as possible. Okay, this is it for this section. Make sure you do enough examples with the derivatives, because it's important to know that the derivatives, at least for the sine, cosine, and tan inverse. The other ones are just consequence. Secant inverse as well. Cosecant and cotangent inverse are just very similar. Okay, so let's stop here.